Hello students, this is my channel Physics Tutorial by Raghunanshu Sarkar, and I am Raghunanshu Sarkar. Today I have come with another lesson on electrostatics. In the previous class we have learned Gauss's theorem, Gauss's law, and also we have done the proof of the Gauss's law. Before that we have also discussed about electric flux, because without electric flux we cannot understand what is Gauss's law. Today we will learn application of electric flux and Gauss's law. That means actually we are about to do some numerical problems on these topics, and before that I am just trying to remember the theory behind those numerical problems that we have to use today. So what was that? Electric flux. What do we mean by electric flux? Electric flux means the number of electric lines or forces passing through a given area normally. Mind it, the electric flux has to be the electric lines of force has to pass normally through the given surface area. If it is not normal, then we will take the normal component of that. Hence, the formula for finding electric flux is phi is equals to integration E dot ds. Ds is a very small amount of area, and hence it is an open area. See, this is an open area. The imaginary area or the real area is the dotted one, and ds is a very small part of that. Now ds area is a vector, and always the area vector is perpendicular to the surface. You know, area vector is always perpendicular to the surface. This is shown in 3D. In 3D it is just like that. The given area is vertically perpendicular to the board, and ds is a part of that, and the ds vector is just pointed normally with the surface. And here our electric field, we have taken arbitrary direction of electric field. Electric field is passing like that. It's an arbitrary angle, it's making an arbitrary angle theta with ds. So we will take the normal component of electric field, since we have seen that in the definition we have shown the electric field has to pass through the area normally. But here the electric field is not going normally, so we have to take the normal component of the electric field, because electric field is also a vector, so we can take the normal component of that. Hence we are taking the normal component of electric field, and it is E cos theta. And E cos theta amount of electric field is passing through that area ds. So the flux is integration E dot ds. We have to integrate because we will vary these ds from in every part of that given area, and we will get the total amount of area, and it will come E ds cos theta. We have to know what is theta, and then we will integrate along the given question. But now, if the area is closed one, closed area means you can imagine a closed area like sphere, like cylinder, or any other given area, arbitrary shape, which occupies certain volume in space. That is a 3D area. When or closed area. When this area is a closed one, the formula is same. We have again we have to take the small amount of area from that is ds, and electric flux will also be found from the normal component of electric field that passing through that ds very small section of area. So we can see in different part of this closed volume or closed area, ds has different directions depending on the curvature of the surface. And electric field, here we have taken a point charge, so the electric field is obviously radially outward. So the electric field also makes different angles with the different area elements ds. So we are just taking one E dot ds, and will then integrate all this area according to the geometry of the given surface. And since integration will have to do on the closed area, so a bubble is put on the integration mark. This bubble just gives an information that the area on which we are doing that integration, the area is a closed one. Nothing changes in the particular mathematics of the integration, but it's just another information that the area is closed one, just putting the bubble on the integration sign. So this is how we calculate the electric flux, how to get the electric flux. And using that electric flux, we have learned in the earlier classes that we can find or we can apply this concept of electric flux in determining electric field using Gauss's law. Gauss's law is a tool which helps us to find the electric field. It actually let us bypass the complicated integration part that we have to do in order to find the electric field in case of Coulomb's law. So Gauss's law, the net electric flux through a closed surface is equal to the ratio of the total charge enclosed and the electric permittivity of the medium. For vacuum, the electric permittivity is epsilon naught. So, and if Q be the amount of charge enclosed by the closed area, then if this amount of charge is Q enclosed, then the electric field can be found by doing that closed integral E dot ds, which will be equal to obviously the ratio Q enclosed by epsilon naught. In the last class, we have also learned certain tricks or certain very important points that we have to keep in our mind in order to apply the Gauss's law. How should be the Gaussian surface? How to choose a Gaussian surface depending on the symmetry or depending on the geometry of the charge configuration. Today only, when we will do the application part of Gauss's law, we will discuss the thing again. So let's start from the very part, the electric flux and the application of electric flux. How we through certain numerical problem, how to get that electric flux, how to find that electric field, or how to get the total amount of charge enclosed by a surface. Let us do certain numerical problems so that these things can be clarified. Okay, students, let us look at this problem. Here it is said the electric field components in the figure, in this figure, that is Ex. That means the electric field is directed along the x-axis, and it is a function of x also, alpha x to the power half, and also it is given that the y component and z component of electric fields are 0. That means there is no electric field vectors in along z axis and along y axis. This is y axis, this is z. So there is only electric field lines in this direction, and the surfaces which is perpendicular to the electric field is shown in the dotted figure. Okay. So how to find, and we have to find the amount of flux through the cube. We know what is the formula for finding the electric flux in the cube, and that is for a closed surface. Since the cube is a closed surface, the formula is closed integral E dot ds. Phi is the flux through the cube, is given by closed integral E dot ds. Now we can divide this closed integral into some open integrals. For that, we can give the names of those surfaces. Let us put the names A, B, C, D, E, F, and G. So GH. So let us split this closed integral into different open integrals. Let me show you. So you can see here the flux can be calculated by expanding this closed integral into open integrals, and we have taken open integrals in each for each surfaces. Front surface, that is AB, GF, then back surface, bottom surface, and top surface. Those surfaces, those which are not marked by the green pens, and the left and right surfaces are also included, and as they are containing the field lines, so they are marked differently from the other sides. All those sides which are pointing towards the y-axis positive and negative, or z-axis positive and negative, they makes an angle 90 degree with the electric field. So all those contributions of fluxes for those sides will be zero, because they are making angle 90 degree angle with the electric fields. But look at the left surface. Here the angle between ds and electric field E1 is 180 degree. This is 180 degree. So the angle is written 180 degree here, and here they have angles between each other is 0 degree, since they are pointing in the same direction. So the cos theta, the theta will be 0 degree here. As we know, cos 180 degree is -1, so it will be E1. E1 is the electric field at this position, because electric field is a function of x. It contains x, so it will be different value. It will have different values in the first surface, left surface, and right surface. For the left surface, it is alpha a to the power half, and for the right surface, it will be a plus s. That means alpha 2a to the power half. And if we integrate ds for both the left and right surface, we will get a square, because it's a cube. It's a cube. Every sides are equal, so the total surface area of these sides will be a square. Hence, the total thing comes like that: E1 a square minus E1 a square minus sign because of this 180 degree angle, and E2 a square. And now I am putting the values of E1 and E2 by placing the values of A and 2A in this equation. We are getting this value and this figure, and this is the total amount of electric flux. So thus we have to calculate the electric flux using this formula, and we have to do the integrations depending on the angles, that makes angles between the electric field and the electric and the surface area. So this is an example of sums, numerical sums. Such sums can be reformed into various for various shapes of closed surface, but the basic thing is just like that. Moving on to the next part. In the next part, we will do certain applications on Gauss's theorem, and also we will do some numericals on Gauss's theorem. So we have our first problem where we have to find the electric field at a point, suppose at this point P, which is at a distance r from an infinitely long charged wire, and the wire is uniformly charged and its line charge density is lambda. We have learned continuous charge distribution, and line charge density means the total charge per unit length, charge per unit length. We have done this problem previously using Coulomb's law, and where we have to do lots of big integrations in order to find the electric field. Now we will do this applying Gauss's law. So first we have to choose a Gaussian surface. To choose a Gaussian surface, certain things has to be kept in our mind. First, what kind of surface should it be? Obviously, the Gaussian surface has to be a closed surface, closed one. Then, the Gaussian surface should be chosen according to the symmetry of the charge distribution. What do we mean by the according to the symmetry of the charge distribution? Because the Gaussian surface should be such that whenever we do the integration to find the flux, because we need to find the flux, Gauss's law states E dot ds equals to q enclosed by epsilon naught, that is Gauss's law. And whenever we have to find that this is the flux, this is the amount of flux, total flux through Gaussian surface. Whenever we have to find the flux through the Gaussian surface, we need to take a suitable Gaussian surface, and we will always keep in mind that whenever we have to choose that Gaussian surface and we have to do that integration, this integration will lead E ds cos theta, and this cos theta term we will always try to avoid this thing, avoid this term, because it will introduce certain amount of difficulty or complexity in our integration. So while we are choosing the Gaussian surface, we will choose the Gaussian surface in such a way that we can avoid the cos theta term. How can we avoid that cos theta term? By just taking theta equal to 0. If theta equal to 0, then cos theta is equals to 1. When cos theta becomes 1, it just merely becomes E dot ds. And thus we can eliminate that cos theta term. Thus we can eliminate cos theta term. And it is very important to eliminate in order to simplify our sum or problem. For this cos theta, what is theta? Theta is the angle between E and S. Angle between E and ds. E and ds. So ds is a small part of Gaussian surface. What is ds? ds, small part of Gaussian surface. And we know what is E is the electric field. So here's the important thing. ds and E must have same direction. In order to become theta equal to, or in order to take theta equal to 0, the most important thing is that in order to make theta equal to 0, in order to make theta equals to 0, E and ds must have same direction. Now whenever we have to look for that, we have to choose a Gaussian surface so that it becomes parallel to the electric field. First, what we have to look for? We have to look for the orientation of the electric field lines, the arrangement of the electric field lines. And as we know, whenever there is a linear charge configuration, the electric field lines are always radially outward. So it's just like the spokes of a tire. It is radially outward in all directions. We only have the radial components of electric field, but we do not have any axial component of electric field. The electric field only has radial components because of such a charge configuration, and it cannot have any axial components. So we need to find such a surface which can provide its surface vector parallel to that electric field. That means the surface itself has to be normal to the electric field, so that the surface vector which is itself perpendicular to the surface become parallel to the electric field. Hence, such a surface, we have cylinder. If we take a cylindrical surface, then this cylindrical surface will provide two types of surface vectors, because a cylinder has two plane surfaces and one curved surfaces, and the radius of the Gaussian surface should be always r, so that it can enclose, you can cover the point P. The radius of the Gaussian surface is r. Let us suppose take the length of the cylinder be L, and we also take a ds which is actually perpendicular. I am showing it like that. Is perpendicular. ds is perpendicular to the curved surface. Also we have another ds's. For this plane surface, ds is pointing in this direction. These are ds vectors. Also, we can have ds in this direction too. So, for this purpose, in order to find the electric field, we must choose a Gaussian surface which is a cylindrical one. So these are things has to be keep in our mind, and for the sum, we're just continuing after that. We have to choose a cylindrical Gaussian surface. Let us choose a cylindrical Gaussian surface. The idea behind choosing the cylindrical Gaussian surface is explained right now. Of radius r and length L. Okay. Now we have to find the total flux, and then we have to equate the total flux with the total charge enclosed. Okay, let us do it. First we have to find the total flux enclosed. Let us find the total flux through the cylinder. What is that? Closed integral E dot ds. Now, just like the previous sum, we are expanding this closed integral into different open integrals. So there are two plane surfaces. So let us write it's a left surface, it's a right surface. Left open surface, plane surface, left plane surface, plane left. E dot ds plus E dot ds again for plane surface to the right, and another surface is curved surface, E dot ds for curved surface. So we have split the closed integrals into open integrals. Now let us check. Is there any radial component of electric field? No. there is no radial component of electric field, so E towards the radial component is 0, or the direction of electric field is in the radial direction, and this is in the axial direction, so they have 90-degree angle between them. So these two will become E ds cos 90 plus E ds cos 90. Since the electric field in the radial direction and these two vectors are perpendicular to the electric field. Electric field is here perpendicular to the surface vector. But for the curved surface, you see, both the electric field lines, electric field is radially outward and ds are also radially outward here, because the curved surface encloses the electric field just perpendicular to it. Hence, it will become E ds cos 0 degree. This is for the curved surface, and this for the plane surfaces, plane left and plane right. These two will become 0 since cos 90 is 0, and the total flux here we get E ds cos 0 means E ds. So the total flux is E ds. Now what is ds? Let us integrate the total curved surface area for the cylinder. If L is its length and R is its radius, then the total amount of this surface area will be 2 pi RL. So 2 pi RL into E. Since here E is constant, because as we have fixed the R, since the R is fixed, so electric field will not change. E is constant, it will come out of the integration, and the total integration will be done only on ds, and we'll get 2 pi RL for that total curved surface area for a cylinder. Now let us equate this with the Q enclosed by epsilon naught term according to Gauss's theorem. I am erasing this part. Okay, take it, note it down. Okay, so the flux is now 2 pi RL E. And what about the Q enclosed? What is the amount of total charge enclosed within the surface? So Q enclosed is not the total charge. Q enclosed is only those charges which is enclosed by the Gaussian surface. So this is the amount of charges enclosed by the Gaussian surface. What is the total amount of charge enclosed by the Gaussian surface? Q enclosed? Q enclosed is, if we know the surface charge density, that means we know the charge per unit length, and also the total length of the Gaussian surface is known. So Q enclosed will become lambda L. Why? For unit length, the total amount of charge is lambda. For L length, it will be lambda L. So it is lambda L by epsilon naught. Equating this, we get E is equals to lambda by 2 pi epsilon naught R. So this is the amount of electric field magnitudically, and if we want to write it vectorically, we'll just have to put an R cap with that, because in the very beginning we have discussed what will be the direction of the electric field, and the direction of the electric field will be radially outward. So the direction of electric field is R cap, since R is a vector along this direction. So thus we can find the total amount of electric field for an infinitely long charged wire. So this is our first application of Gauss's law. And one thing here we can note that we know the electric field for, we have also learned this before. Again we are discussing this thing that we know electric field for a point charges varies with 1 by r square, but for this infinitely long wire, electric field varies as 1 by r. So fall of electric field, the rate of decrement of electric field is much less than that of point charge. Okay. Now moving to the next part of application, and now we shall find the electric flux for infinitely long charge plane. So here is our problem. We have to find the electric field at point P. Let us suppose this is a very large plane containing charges. The uniform surface charge density is sigma, and we need to find the electric field at a point P. So first of all, we have to find the Gaussian surface, and in order to find the Gaussian surface, we have seen in the last video that we need to find the direction of the electric field. And depending on the direction of the electric field, we have to choose the Gaussian surface in such a way that the direction of the electric field and the direction of the surface vector for the Gaussian surface has to be parallel to each other, so that we can eliminate the cos theta. This is the basic principle. And for that, what kind of surface should we take? Let us taking a cylindrical surface. Again, that cylindrical surface. Taking that cylindrical surface, and the cylindrical surface must be such that it can enclose the total charges. We have to enclose the total charge. Now imagine we have a page, and the page contains charge. Suppose we have a page. We have a page, this thin sheet, this represents that thin sheet, and that page contains charge. Now up this page, this is a single page, suppose this is a single page, and this page has two surfaces, and both the surfaces contains charge. Hence, when we have to enclose the total surface, we need to enclose it from the top and as well as from the bottom, so that the total charge can be enclosed for that particular region. So whenever we are drawing the Gaussian surface, maybe that surface be cylinder or whatever, we must extend the surface in both upward direction, that means in the top or in the bottom. In both top and bottom, we must extend that surface so that this surface can actually enclose the total charge within this area. And both the lengths in the above and below the surface will be same, must be same. Now let us, why we have chosen such cylindrical surface? Because of if we see the electric lines of forces, the orientation of electric lines of forces, the electric lines of forces are like that. It is vertically perpendicular to the surface. If we place a coordinate, say this is z-axis, this is x-axis, and this is x, y, z. Suppose this is y-axis. So the electric field is in the y-axis direction. Electric field is always y-axis direction. It can be a positive y-axis direction or it can be negative y-axis direction. Okay. So no other components of electric fields are there. Electric field is only in the y-axis, positive and negative. That is why we have chosen this cylindrical surface, because for that cylindrical surface, this cylindrical surface provides two types of area. There are two plane surfaces at the top and at the bottom, and there is a curved surface as well. We can take the small elemental area on all those surfaces. That means ds. Taking ds in the upward direction, also taking ds in the downward direction. There is also ds along the curved surface. So let us bring it like that. Okay. Now the second step to find the net flux. So let's find the net flux through the surface. Net flux phi is obviously equals to closed integral E dot ds. This is the net flux. And whenever we are doing the finding the net flux, we need to expand this along two plane surfaces and one curved surface. So plane surface at the top, E dot ds plus plane surface at the bottom, plane at the bottom, and the curved surface. Now look at the figure. For both the top surface and the bottom surface, the direction of electric field and the direction of ds vector are same. That means they are making 0 degree angle. So we have E ds cos 0 degree for both. Look at the direction of electric field also reverses below the surface, no? So there will not be 180 degree like the previous sum, because the direction of electric field and the direction of surface is same in both the cases of the flat surfaces, plane surfaces. And for the curved surface, there is no radial component of electric field, or hence the electric field and the ds making 90 degree angle. Electric field and ds making 90 degree angle. So we can write E ds cos 90 for curved surface. That is top and bottom plane surface, and this is curved surface. Curved surface goes to 0, and the plane surfaces will contribute to E integration ds. Because E is constant, we need to integrate only on ds. Now this is the total amount of flux net. Now writing this value of flux net in case of Gauss's Gauss's law. From Gauss's law, we have phi net equals to q enclosed by epsilon naught. That means 2E integration ds is equals to, now what is the amount of q enclosed by that surface? If this cylinder has an area of A, it will be sigma A by epsilon naught. Actually, we can write like sigma dA, integration sigma dA, and after doing that integration we will get A. dA or ds, whatever, we can write sigma ds 1 by epsilon naught, because q enclosed is sigma ds. This is q enclosed. If we integrate this small area, this is the small ds area, this ds area, and we can also have this ds area over here, and we can integrate that ds area part by part, small part by part, and integrate the total area. We will get the total area A. If it is infinite, then it will be infinity, but we are now putting A in both the cases, and we are getting 2EA equals to sigma A by epsilon naught. So from this, what we get is E equals to sigma by 2 epsilon naught. sigma by 2 epsilon naught. If we put the vector sign, then we will have to give the direction of electric field, and as we have chosen the direction, as we have chosen the point in the upward direction of the plane sheet, and the direction will be of the electric field is here j cap, positive j cap. So I am writing j cap to represent the direction of the electric field. Hence we have got the value of electric field for infinite long plane or large plane sheet containing a sigma amount of surface charge density. And one important, very important thing what we can note here, that the electric field is constant. It's a constant electric field. It will not vary with the distance. It will not vary with the distance. We can see there is no term containing the distance, so that it becomes a function of distance. How can this be explained physically? Previously we see that whenever the charge distribution is along the wire, linear charge distribution, the electric field falls, and of course the charge distribution extends up to infinity. Then the electric field falls with respect to 1 by r, inversely proportional to r. And here, when the charge distribution is in 2D, that means along the infinite long sheet, the electric field becomes constant. That means, as we are going further, we are having a particular solid angle or having a particular angle of projection. We are gathering more and more charges. For linear, we are getting charges in the one dimensional, and the electric field is falling in 2 dimensional. As a result, it counterbalances each other, and the electric field finally falls with 1 by r. As because it is 2D, and when we are going further from the sheet, and for a particular projection, the charge is accumulating more and more in 2D, and the electric field is also falling 1 by r square. It means it has a tendency to fall 1 by r square, because Coulomb's law is the inverse square law. So both of them compensates each other. The increment of the charge accumulation and the falling rate of electric field is same, so it will remain constant as we go further from the sheet. So this is the electric field for infinite long charge plane. We can also modify this particular derivation into certain tricky thing. Let us see that. Let us modify the previous problem in such a way that we have 2 plane sheets, long plane sheets. One is positively charged, another is negatively charged. They are placed side by side to each other, and we need to find the electric field between them, and also 2 ends of them. That means E1, E2, E3. In all these 3 zones, we need to find the electric field. How can we do that? We know what is the electric field for plane sheets, and we will apply the result directly. As you know, that electric field at each side of long or large charge plane is sigma by 2 epsilon naught, where sigma is the surface charge density. Okay, and it is for each side. Remember, it is for one side only. So let us draw the field lines. For positive plate, field lines will be directed outward from that. Always field lines are directed outward from the positive plates. For the negative plates, field lines are inward. So they come from infinity and meets at the plate. Now Will there be any component of electric field in this region for negative plates? The answer is yes. There will be electric fields too for negative plates in this direction, and its direction will be inward, that means towards the negative plate. Similarly, there will be the components of electric field or field lines for positive plates also in this third region, and it will be again towards the outer direction, because it tends to go away and this tends to come in. Now since the electric field does not depend on the distance from the plane sheet, so the value of electric field for the negative and for the positive will be same in all the parts of that, all the zones. Okay, electric field for negative is always sigma by 2 epsilon naught, and electric field for positive is always sigma by 2 epsilon naught. Now in this region 2, both the electric field is directed in the same direction, so they will be added. And for the other two regions, these two electric fields are opposite to each other. Since they are opposite to each other, so the net result of these electric fields will be, for E1 it is 0, zone 3 it is also 0, and for E2 or zone 2 it will be sigma by epsilon naught. So finally, if we have two plates like that, one is positively charged, one is negatively charged, there will be only electric field between them, and that is sigma by epsilon naught, and no electric field outside those planes. So this is the result. We'll actually apply this thing in case of finding the capacitance of a parallel plate capacitor in the next chapter. Okay, so let us move into the next part. We'll find the electric field for spherical body, spherical object. So here is our next problem. We need to find the electric field for thin spherical shell. Now spherical shell means it is empty, it is hollow inside, and it has a very thin layer or very thin circumference, and it's a uniformly it is uniformly charged, and of course the charge will remain uniformly distributed on the surface of the sphere. Since it's a closed surface and it's a finite amount of area, unlike the previous two cases where the area or the lengths were infinite, so we can also take the total charge for that sphere. Let us suppose the total charge for the sphere is Q. Total charge Q. For the previous two examples, for infinitely long wire and infinitely long plane sheets, their total charge cannot be calculated because it is infinite. If we need to find the total charge, it will again be infinity at that point. But for this, since it is a finite dimension, so we have total charge Q. We can write that. We need to find the electric field. First outside, let P be the point outside the sphere, and let the distance of P from center is R. P is the point. The distance from the center is R. Here R is greater than small r is greater than capital R, outside, for outside. Whenever we have to apply the Gauss's law, we need to first see whether what is the direction of the electric field for this, and the electric field will be obviously radially outward. As if, we'll see later, the spherical, sphere, the hollow sphere can be considered as if the total charge is concentrated at the center. We'll know it at the end of the derivation. But for now, the direction of the electric field is radially outward. This is the direction of the electric field. So we need to find a closed surface such that the surface vector will be perpendicular to the surface vector is parallel to the electric field, and for that purpose we will use a spherical Gaussian surface. And as we need to find the electric field at a point P, let us give this point is P, and this amount of distance is R. So the Gaussian surface will be a spherical Gaussian surface of radius R. Let us draw a spherical Gaussian. So this one is the Gaussian surface, spherical Gaussian surface. Why we have chosen spherical Gaussian surface? Because if we choose spherical surface, then the surface vector or ds will be in the direction of the electric field. So the direction between them will be 0, theta will be 0, cos theta can be eliminated. Now, second step, we need to find the net flux. Net flux is given as closed integral E dot ds. Let us directly apply the Gauss's law. Okay, let us directly apply the Gauss's law. From Gauss's law, E dot ds equals to q enclosed by epsilon naught. Now E is constant since R is constant. So E comes out of the integration and we need to find the total. Of course, E dot ds become EDS since the angle between them is 0 degree. So we need to write this line again, cos 0 degree. What is Q enclosed? Q enclosed is the total amount of charge enclosed by the Gaussian surface, and the total charge is being enclosed by the Gaussian surface. So Q enclosed is Q by epsilon naught. As we have taken the total charge is Q. E goes outside of the integration. ds is the amount of small arbitrarily chosen area. We need to integrate all those ds over the total Gaussian surface, and q by epsilon naught is a result of that. Now, if we integrate the total Gaussian surface ds by ds, total Gaussian surface, what will be? What we will get? We will get the total surface area of the Gaussian surface, and the surface area of the Gaussian surface is 4 pi r square, since r is the radius of the Gaussian surface. Of radius r, and q by epsilon naught remains as like that. So electric field becomes 1 by 4 pi epsilon naught q by r square. Sorry. If we need to give the direction is obviously outward in the direction of r cap. R cap is the unit vector pointing outward. So we see the electric field here obtained is exactly equal to the electric field for the point charges if the total charge is being concentrated at the very center, and if we need to find the electric field at a distance r from that, then we will also get the same electric field. So whatever I was telling previously, that for the electric field of a spherical cell, outside of it is exactly equal to the electric field of a point charge placed at the center of the spherical cell, and both the electric fields at that very point will be same, both magnitudically and direction wise. So instead of a spherical cell, we can assume that the total charge is being concentrated at its center. We can assume like that. So this is the electric field outside of the Gaussian surface. Outside of the spherical cell. Now we need to find the electric field on surface. On surface means on the surface of the sphere. If we have to find this electric field at the surface of the sphere, what we will do? We just decrease the radius of the Gaussian surface, so that the Gaussian surface tightly fits on the surface of the sphere itself. Then the radius of the Gaussian surface will become capital R, and if we replace small r by capital R, we will get the electric field at the surface. So electric field at the surface will be 1 by 4 pi epsilon naught q by capital R square r cap. Because at surface R is equals to capital R. So this is number 1, this is number 2. Now we have to find the electric field inside the spherical surface. In order to find the electric field inside the spherical surface, what we will do? We will do the same thing. We will just decrease the Gaussian length of the Gaussian surface furthermore. So for that purpose, we need to take a new Gaussian surface, and suppose now R is this amount of radius R, passing through the very point where we have to find the electric field inside the sphere. For inside the sphere, the Gaussian surface has just gone inside. The Gaussian surface has just gone inside the given spherical shell. The electric field is still radially outward. The direction of the electric field is still radially outward, and we need to find the electric field at this particular point inside the field, inside the sphere. For this, everything in the left side remains same, but one thing will change, that is the Q value of Q enclosed. Now this Gaussian surface, this particular Gaussian surface does not encloses any amount of charge within it, because the charge is at the surface, because it is a spherical cell. Inside it is hollow, so there is no charge inside the sphere, so it will enclose nothing. Q enclosed will be 0 instead of Q, because it is not enclosing any amount of charge. Everything is same, and as the right hand side is 0, we have it is 0. Hence, the obvious result of electric field inside the Gaussian surface is 0. Inside the Gaussian surface, inside the spherical cell. Inside the spherical cell is 0. So thus we see that electric field outside is non-zero. Electric field on surface is maximum, because capital R is the smallest value of small r that can be possible. And when R is less than capital R, then it becomes 0. So there is no electric field inside a spherical shell. There cannot be any electric field inside a spherical shell when the charge resides, stays at the surface. That is called electrostatic shielding. If we represent it graphically, it will look like that. If we show the variation of the electric field with the distance from the center to the radius, So this is the amount of distance from the center to the radius. Electric field is 0, and at the surface, this is the surface, electric field is maximum. This is electric field, and this is R. The maximum value of electric field is 1 by 4 pi epsilon naught Q by R square, and then it falls. E is proportional to 1 by R square. So, and it becomes parallel to the asymptote to the x-axis or r-axis. So this is the graph which represents the variation of the electric field with distance from the spherical shell. Now the result is same for the conducting solid sphere as that of spherical shell. Why? Because again a conducting solid sphere will conduct all the charges to the surface, as because the surface charges has a natural tendency to go outside and stay at the surface of a body. So there will be no charge inside a solid conducting sphere. So for solid conducting sphere, the variation of the electric field is just like that of the spherical shell. But that is not for non-conducting spherical solid sphere. For non-conducting solid sphere, there must be electric field inside the sphere too, because here the charge stays. In the next session, we'll learn for the non-conducting solid sphere. Okay, so this is all about today's lesson. We have just discussed certain applications of Gauss's law, and in the following session we'll learn more numerical sums based on Gauss's law, and also the electric field for non-conducting sphere. Thank you.